Hey folks, I've got another torque example for you. This one is actually a demonstration that I'll often do in class. So if you happen to be in class and I'm able to do it, you'll see it. Um, but for now, I'm going to recreate it on paper. So it's very simple. I have an old bike wheel. It's actually from an old stroller. It's a stroller wheel, and I hang it by a string, and I put a scale here to measure the force that the string exerts on the stroller wheel. And then I wind some string around the rim of the stroller wheel and I hang a little mass off the end like so. Okay. And I actually have real life data here. The mass of the wheel is about 480 grams. The moment of inertia of the wheel is this number here, 0.00326. It's really small because it's an aluminum wheel and it's mostly spokes. So this number is pretty small. It's got a radius, and then the mass I'm hanging off the edge is 200 grams. Okay. And basically, I have a series of questions for you. And this one is going to involve numbers. So we will pull the calculator out on this one. So when this thing is stationary, so like let's say I attach the string right here so it can't unwind or anything. So when it's stationary, what does the scale read? Okay. It's going to be a real easy one. Okay. And then when I let it go, what's going to happen? Okay. And what are all the forces acting on the wheel? Okay. And what's the acceleration of the block, etc. So we're going to determine when I let this thing go, what's the acceleration of the block, what's the angular acceleration of the wheel, and what force does the scale read while this little guy is falling. Okay. Now, the first part of this is when it's still. Okay. So I'll do that over here. Well, by the way, if you need a moment to copy the diagram and the data, I would take that moment now. All right. So if the wheel is still, like you've pinned it, like you put a little thing here so it can't unwind. All right, let's draw an FBD. So here's the wheel, here's the little mass hanging over the edge, and you're going to have the force. I'll call it Fs for scale. It's a tension force, but we'll call it scale. What's the force of that scale? Oh, and the pulley has a mass big M. Okay. Well, this is pretty easy. If I draw FBDs I've got two objects. I've got the pulley itself, which is going to have the force of the scale, its weight, which will be big mg, and then it'll have the tension of the little guy pulling down on it. And then the little dude, he's going to have that same tension holding him up, and he's going to have little mg. Now, hopefully in this case, if it's still, you'll understand that the tension equals little mg, okay, if it's still or not accelerating. So in that case, the force of the scale is going to equal big mg plus that tension, which is little mg. So the force of the scale would simply be big mg plus little mg, okay? And we're going to throw a number at that. So big M is 480 grams, should be 0.48 kilograms. I'll actually put the masses together, plus the little mass, which is 0.2, and then multiply that by g. And the force of the scale I get, just so you have an idea here for numbers, I get 6.664 newtons. Okay, so that's the weight. Basically, it's the weight of the wheel and the little mass. That's what that scale is going to equal in this case. All right, so that part's easy. Now for the fun part. So now we pull this little pin out or whatever, and now this weight is free to fall. Okay, so it's gonna unwind this string and make the pulley angularly accelerate. So the several questions we have is, what is the angular acceleration of the pulley? What's the linear acceleration down of this mass? What's the tension in this string? And what's the scale force? Now, one prediction that I would have you make is, while this thing is unwinding, what's the scale going to do? Is the scale force going to be more than this 6 point whatever, equal to this 6 point whatever, or less than this 6 point whatever? So what's going to happen to that scale force when this thing is unwinding? All right. So in your mind, make your prediction. What do y'all think? Okay. All right. Let's try it out. So now it's moving. I'm going to kind of cordon this work off. So we still have our two FBDs. We have the pulley. We have force of the scale up. We have this tension down, and we have big mg acting down. Okay. And then we have the little weight, little m. Okay. And now we have a little mg down, and we have tension up. Now, hopefully this time you recognize that little mg has to be bigger than tension because this dude is accelerating down. And I'm going to go ahead and call down positive. In other words, for this system, okay, we're going to say that we know it's going to unwind clockwise. So I'm going to call that direction positive, okay? So for the little dude, we have Newton's second law. We're going to do net force equals ma. Well, the force would be little mg minus tension equals little ma. Now, unfortunately, we got two unknowns there. We don't know tension, nor do we know acceleration. But then I look at the pulley, and there I'm going to do net torque equals I alpha, okay? Because it's rotating. It's not moving up or down or anything, but it is rotating. Well, what's the torque? Well, it'd be R cross tension. Now, the other two forces, mg and the force of the scale, neither of them are causing torque because they both act through the center, through the axis of rotation. So their perpendicular lever arms are zero. So they're not going to make the thing spin. The only thing that makes that pulley spin is the tension from that string. And this is going to equal I, which I've given you. And by the way, remind me, I'll explain to you how I know the moment inertia of the wheel in a little bit here. And then alpha. Well, alpha, I know that A tangential equals R alpha, okay? So I'm going to get rid of alpha by putting A tangential over R. And in these equations, these are the same. These accelerations are the same, okay? Now, the one last thing I'll do is I will divide both sides by R here. So I've got tension equals I A divided by R squared, okay? So now I have two equations with two unknowns, A and T. So what I'm going to do is I'm just going to add the equations together. So on the left side, I got a positive T, I got a positive little mg, and I got a negative T. So the T's drop out. So I get little mg equals, on the right side, I'm going to factor the A out, and I have a little m plus an I over R squared. And if I solve for the acceleration, I get little mg over little m plus I over R squared. And I have numbers for all of that stuff, right? Little m is 0.2, g is 9.8 over, on the bottom, I've got 0.2 plus I, which is that really small number I gave you guys, 0.00326. So 0.00326 over the radius, which is 14.75 centimeters or 0.1475. And I got to square that radius. And if you do all that, I get an acceleration of, my calculator spits out 5.60 meters per second per second. So that's the downward acceleration of this little block right there, okay? You can also find alpha. Alpha would just be A over R. You would take 5.6 divided by 0.1475 and you get a number. I'm not even going to bother plugging that in. It'd be pretty easy. Oh, the tension. Okay, so once we have the acceleration, you can plug that back into either equation. Yeah, I'll use this one. So if I solve for tension there, it's going to be mg minus ma, or simply m times g minus a, and m is 0.2 kilograms, and we just got a, and if you plug that in, I get a tension of 0.84 newtons. Okay, so there's my tension in the string, this tension while the block falls. And then the final question I asked you guys is, what force does the scale have on it now? And how does it relate to the force we had when the system was still? All right. Well, the pulley, while it's rotating, it's not linearly moving anywhere. It's not moving up or down or left or right. Okay. So I know that on that pulley, the net force still has to equal 0. Well, what's the only thing that's changed? Well, our tension has changed. Okay, before it was equal to little mg. It would be 1.96 newtons. Okay, well now it's only 0.84 newtons, so it's gotten less. Okay, so right away I know the answer to my question. The scale force is going to be less than it was before. Okay, and you're going to have the force of the scale is going to equal big mg plus that tension, which is 0.48 times 9.8 plus my tension, which is 0.84, and I get the new scale force is equal to 5.54 newtons. And when I do this demonstration in class, we actually can see it. So it drops by over 1. So the scale, you'll see like the needle, and when I let the little weight go, the needle actually moves to the left a little bit. The scale reads less force while this thing is falling. Okay. Now, a couple notes about that. You can answer this question. The question is a scale force more or less the same. You can actually answer it without calculating any of this stuff. When you let this system go, some of the mass is accelerating down, the little guy. So we have some mass accelerating down and no mass accelerating up. So what that means is the overall downward force has to be bigger than the overall upward force. On the system, the two downward forces are the two weights, big mg and little mg. There is tension in there, but if you look at the system and you were to add all these forces together, these tensions cancel out. Okay, so the external forces to the system are big mg and little mg down, and the scale force up. Well, since I have some mass accelerating down, the two mg's added together have to be bigger than the scale force to produce a downward acceleration of any kind. Okay, so that's like a logic question. If you saw that kind of question on a test, you should be able to answer it without doing all these crazy calculations. You can hopefully just reason your way through it. The last thing I'll mention here is, how on earth do I know the moment of inertia of this wheel? Now, by the way, this wheel that I have, it's an old wheel of mine, and it's not a disc, it's not a hoop, it's something in between. It's got spokes, it's like a bike wheel. That's what it looks like. So here's what I did. I did this problem in reverse. I dropped this weight and I timed it falling through a distance. Then I used that distance equals 1/2 AT squared to calculate the acceleration. And then I backtracked through these equations and I was able to calculate the I, moment of inertia of the wheel. So it was a different unknown. Basically, it's the same exact problem. It's just a different unknown now. Instead of not knowing A, I didn't know I, and I was able to work my way back and calculate I. So this would be a good lab question, like, hey, how would you figure out the moment of inertia of a wheel with this apparatus? So you'd measure the acceleration by measuring time and distance. You actually would calculate the acceleration by measuring time and distance, and then you would set up Newton's second law of rotation for the pulley and Newton's second law of motion for the mass, and you would eliminate tension in those equations, and you would solve for I. Okay, and basically you would get this equation right here, and you would just get I by itself, and the radius, you can measure that, the little mass is 200 grams, and you have figured out A from timing it through a distance. So that was the first example I think I did with numbers in a little bit. I hope it was helpful, and thank you very much.